number two webinars will be chaired by Professor Hu Qiang of CNC, China. She's the leader. She's the chairperson of the strong earthquake working group of the AOGS, and she will be chairing the next two talks one by Professor Hao Manzhou, and then to be followed by another talk, both 45 minutes with 15 minutes Q&A, to be given by Professor Zhonghan Zhang of the National Central University, and afterward, we hope that we have a maybe 10-20 minutes discussion, by the Q&A dialogue between the two speakers and also the audience, talking about maybe we will plan the number 3 webinars very soon, but let's start our number 2 first. Professor Huang, is all yours now. Thank you.
Okay, thank you for your introduction. I think this is our second webinar of Strong Earthquake Working Group. I have a short introduction to this webinar. Here we can have a small topic for this webinar: taking proactive measures while coexisting with the earthquake risks. This is from the earthquake experience of Venezuela. Venezuela, the very strong earthquakes induced the buildings, tall buildings, crashed. So I use this topic to do today's introduction of the webinar. And this is a global earthquakes with since 2024, the magnitude is more than 7. Before AOGS 2024 in Korea, there were 3 strong earthquakes within 4 months occurred nearby here, Japan, and Taiwan Island, and Xinjiang Autonomous Region. So many earthquakes occurred. What we can do? Why we should have proactivities? We should take proactive activities to measure the earthquake assessment, maybe. So even though earthquakes cannot be precisely predicted, we should not sit still and wait for the measures down from the sky. So I proposed a working group on strong earthquakes during AOGS 2024 in Korea, and got permission from Professor Wen Xun. Then we have the third working group of AOGS Regional Advisory Committee, and called for participants from the conference in Korea. And this is the earthquake here. Is very frequently occurred near the mainland or island. The local people, we get the proposal in Pyeongchang and have the working group in Singapore, and began online seminars since August 2025. And till now, we called for members from participants who are interested in earthquake researches since August since AOGS 2023, and also get more participants from AOGS or widely related to earthquake researches. And online seminars on earthquake monitoring, modeling, and source geodynamic models have held. And online discussions on emerging issues, anomalous phenomena related to recent big earthquakes, similar to today's online webinars, is also held. And since August 2025, there are 4 online seminars, 2 of them relevant to earthquake monitoring from satellite and from ground base. 1 online seminar is related to rupture modeling from slow slip to super shear. And 1 online seminar is relevant to geodynamic model, the phasal models during earthquake rupturing. And 1 online conference on Myanmar earthquake was joined in, and 1 webinar. The next great one first had been held on May 20th. And today we are the second one, and we try to have the third one and call for speakers. This is today's. Now, after earthquake in Japan, we get some co-seismic changes in volume stream 1 stream meters in eastern China. This earthquake is also very strong, but we can get the steps, stream meters steps. Well, the steps are induced by seismic wave propagation. You can get the information from the data. And the amplitude different with stations. In a whole, the amplitude were not too big. But the second one, in this year, April 20, the position is not very far from Chinese mainland, but the steps of the stream meters is very, very obvious, very too big. Well, the very big stations, many are along the Tanlu fault zone. It's very strange. Big fault zone. Firstly, please note the big fault zone is more sensitively than stable zone. Yes. And this is third one in Taiwan. The steps is also, and the stations is more than in Japan. And the obvious stream changes is also along Fujian and Tanlu faults. It's especially the fault zone area is more sensitive. And this is the Myanmar earthquake. Myanmar earthquake, we get more information from North China to East China and to Southeast China. Especially, we get a pre-stream release in Yunnan province. in Yunnan province is the very active areas. It's nearby Myanmar earthquake nearest regions, stations. This is pre-release of this volume stream meters several hours before earthquake occurrence. So I think this is the why we invite the Professor He Manchao to show his Newton force. The Newton force is for imminent earthquake prediction precursor. So this is nearby the fault zone. We can get the pre-release of stream meter. This is the stream, but today Professor He will show the Newton force along the fault. So it's more context or relationship between the stress and strain. Well, it's two concepts of this. This is the Newton force and this volume strain. What's the bridge between them? Please use these figures, data to keep thinking about today's speakings. I show this data to arouse your thinking about what the bridge before Newton force of the fault zone and the stream meter release right before earthquake occurrence. So especially this is the very strange pre-release streams registered in Yunnan province right before Myanmar earthquake occurrence. And then this is Venezuela. Venezuela's earthquake occurred, but the registration information is quite different. Maybe it's far from mainland. Maybe it's more hidden information. I don't know, but we can get more hypotheses for the global response to strong earthquake. This is only one case recognized the steps. The local station get the recording of abnormally air pressure changes. During these steps, there is abnormal air pressure changes. But right after earthquake occurred, and also right before earthquake occurred, what the causes and the results between these two phenomena, air pressure changes, earthquake far from the stations. So long-range correlation is the physics. What's the physics nature behind the long-range correlations? Okay, so what's the idea about this phenomena? And welcome to keep contact for cooperation. This is the proactive measures for observation. And today, this is a great honor today for us to invite academician Professor He and Deputy Director Professor Zhang to show their proactive measures taken from their work position. For Professor He, Newton force monitoring system right before earthquake occur or right before the fault slip. So I think it's a new approach to imminent earthquake prediction because we observed the pre-stream meter release right before earthquake occurred. So it's very similar, but it's a different concept. What the nature of the physics between these two approaches. And for Professor He, it's the innovative idea from challenges of mechanical engineering, where his lifetime to research. And we have the second Professor Dan towards the resilience communities, developing seismic risk and early warning research. If in Venezuela, such research is the similar developed, so maybe the high building or tall building will not crash disastrously like that. It's the progress of this monitoring network of seismograms development and statistical seismology in Taiwan, the very active areas of the world. So the proactive measures taken in the inner area is completely the disasters will reduced. We cannot prevent the earthquake occur, but we can take proactive measures to prevent the disasters of the earthquake. So today's taking proactive measures while coexisting with the earthquake risks from long-term strong building design and from to imminent earthquake prediction. Okay, I think it's very a great honor for us to invite two professors to get their extraordinary works from long-term to imminent term. Okay, I think I use the time to too much, but I think need more time to our speakers. Okay, now please, Professor He.
Ladies and gentlemen, good afternoon. It's my honor to say something about Newton force monitoring system, new approach to imminent earthquake prediction. Several parts will be included in my presentation. And firstly, say something about the research background. Try to give us some problem, scientific phenomena happened after or during process of strong earthquake. What means a strong earthquake? The magnitude is larger than 6. And according to those problems and the phenomena happened in strong earthquake, we set up a double block mechanics model. We try to set up a model for double block mechanics. Later on, we can give an explanation about it. What is double block mechanics model? But after that, we gave a monitoring system concerning the Newton force measurement. And according to many curves, not only for the earthquake, but for the landslide. So according to the monitoring system, we gave several cases to be practiced. That means application. So at last, I gave several words to mention something about the conclusion. And here is the research background. Why we study the earthquake? You can see this map. From Arabis to the Himalaya, this is west to the east, 10,000 kilometers long, shows the tectonic zone, which is also the earthquake zone. And from this photo, we can know that from the Arabis to the Himalaya, a lot of earthquake happen there. And it is a earthquake zone. And also it shows a linear distribution. Not only this, but also the earthquake along the Pacific plate. So the difference is that in Himalaya area, it's not the linear zone. It's a group. It's an area. The distribution of the earthquake shows a different way. That means earthquake frequently occurred in those areas. According to the statistics from the 1900 to the present, here the strong earthquake is about 139 times. That means at least once a 1 year. So this is so-called the producer of strong earthquake. So we need to research something about earthquake here. What is a scientific, the common scientific phenomenon for the strong earthquake? We just mentioned strong earthquake means the magnitude larger than 6. And here is the case 1, shows the San Francisco earthquake happened in USA. Magnitude is about the 8.6. It's a very large earthquake. And after earthquake, you can see the picture show the very large displacement of a shear along the X2 fault. So this is very, I think it's a phenomenon. It's a scientific phenomenon for strong earthquakes. But if the earthquakes, the wake, maybe less than 5, maybe no obvious displacement of a shear appeared in the surface. Maybe it is a special phenomenon for the strong earthquakes. So this is, and also another case to show in Jiqie earthquake, Taiwan in 1999. magnitude is about 6.6. So you can show the gentleman there, the shear displacement, the very large scale, maybe about near the 2 meters, I think. Also show a phenomenon, a large shear deformation. And also Wenchuan earthquake, very strong, is a magnitude about 8.0. Happened in 2008. The photo shows people point to the shear, very large shear deformation, about 4 to 5 meters there. As the people is me. At that time, I'm much younger. So there's also a special phenomenon about the large scale shear deformation. So next one happened in Turkey. I have been there to do the field investigation. Turkey earthquake happened in 2023, 23rd magnitude about 7.8. So you can say it's more 1 meter shear deformation. So this is situ. So we have a lot of data to show that for strong earthquake, have very large deformation appeared in the surface, but for the wake, a smaller earthquake, not this phenomenon. So we can say it is a common scientific phenomenon of a strong earthquake. That means a very large shear deformation along the fault plane. So this is a case. This is a key point I want to say. And another point is that if earthquake happens, earthquake is a process of dynamics. So a strong earthquake, not only strong, but if it is an earthquake, should obey the Newton's second law, because it is a dynamic process. And the Newton's second law is no linear dynamic equations. And so we need to research about the Newton force variation along the active fault. But before, we always observe the deformation or displacement. We did a lot. And for deformation or displacement measurement, which discovered in 1923 by Taiwan. For 100 years past, we measured a lot of data and a lot of curves to show the deformation regulation. But we failed to prediction, to give a correct, reasonable prediction for the earthquake. So if we even the Newton force can describe the process of earthquake, but the Newton gave a propose about this formula. But if we study the earthquake, we still have some problems. We should research deeper and deeper. First, when is a Newton force produced? This is if the Newton force produced after moving. That means we couldn't use the Newton force for prediction. If the Newton force occurred before moving, before earthquake happened, and we can use these parameters to obtain the precursor of earthquake. So this is the first problem. A second problem, what is the precursor for earthquake disaster? If we can get the process of variation of the Newton force variation, and what is the precursor in this curve? So this is the second problem. It should be done by our research. And the third problem is how long is the interval time between the precursor and the disaster. So we need to clear those problems. So in order to have a solution of the problem, we have to set up a double block mechanics model. The model here shows that areas for potential earthquake, the crust should be divided by active fault. That means those active fault will induce the earthquake. And the hanging wall and floating wall. So this is means double block. And also not only the active fault, but also the slip surface for landslide. The slip surface divides the rock masses of slope into two blocks, the sliding body and the sliding bite. So there's also the double block mechanics. So both are similarity for boundary mechanics. We always measure the point whenever the which always in the block. For example, Professor Huang just shows the strain measurement. What means a strain measurement or stress measurement? That means something happened at a point. But the difference, what is the difference between the Newton force and the strain stress? The Newton force is a joint force because of many types of forces acting on the surface of active fault. For example, the shear, the sliding force, and friction force, and normal force, so on and so forth. So many forces are acting on the surface. But what is Newton force? Newton force is a resultant force. That means joint force. Among this resultant force, among the forces acting on the surface of active force. So active surface. So active fault surface. This is different. And so two models for earthquake and for landslide is very similar. So we studied the double block mechanics. Always use two models here. So start from the double block model. And we have to use the mathematics to give a formula how to get the Newton force according to the formula for earthquake and for earthquakes, lower one for the landslide is the upper one. And after mathematics research, we should give a physical experiment how to get the Newton force variation curves, and also can we find the precursor in the curves. Just now, we give an experiment process. Those experiments have been done in my laboratory in 2006. And even it's an old experiment, but I think it's belong to fundamental studies. And what is Newton force? Newton force is between the red color one and the black color. It's joint forces. And the red one shows a sliding force, and the black color one shows the resistant force. So Newton force is a joint force between two. And the variation is showed in the red corner. And you can see what is the precursor. If we see the process curve carefully, we can find that precursor is a dropping of Newton force. This dropping happens, the moment of dropping, sliding doesn't occur. Wait a minute, and then sliding happened. That means the precursor happened first, and then sliding happened. So dropping is a precursor. Let's do the earthquake. Earthquake is a fault, active fault. Physical experiment of the earthquake process, you can show that we have got the two curves for first active fault and second active fault in different colors, red color and green color curves. And to the first fault and second fault respectively. This model is the Wenchuan earthquake model. And you can see that also the same phenomenon about the precursor, dropping. After dropping, you can see the vibration of a curve to show the earthquake. And before vibration, before earthquake, you can see we have a time, then the dropping happened first. And then at a moment of dropping, no vibration. And wait some time, then earthquake happened. So it's really the precursor. Precursor is dropping. In different shape of curves to show different properties of different roughness of fault plane. So this is a key point to show our expert here. And so according to the two experiments, we set up standard curves of the model for Newton force variation. And I think the process of earthquake, the landslide, this is a standard curve for that. And at the beginning, if a false earthquake is a mechanics process, so several forces acting on the rock masses or crust. Firstly, is a linear deformation to become a process of deformation. Early of a deformation is about the linear deformation. And then no linear large deformation happened. And then bifurcation, and then cross, and then broken. And after broken, the motion happened, the movement happened. So this is a process for earthquake or for the landslide. So we always describe something by calculation, the fundamental equations, always depend upon the Newton force, and then it depends on the deformation, Hooke's law. If a movement, we should obey the Newton's law. At the linear state, we should obey the Hooke's law. But the main ideas and is useful for earthquake precursor studies. We should pay attention to the dark area. The dark area is very potent because here maybe several characteristics about the dynamic happen. For example, large deformation and bifurcation cause and broken happen in dark area. So also precursor maybe happen here. So we need, firstly, give a description of the mathematics about the dark area. And then we should do the physical research, how to measure the curves happened in the dark area. Fundamental study here also should give a relationship between the Hooke's law and the Newton law. What's the relation between two? So maybe something should have a solution here. So this is what we thought before. After several years of studies, we finally give answer about it. First formula to give Newton force generation. That means before moving, Newton force occurred. That means Newton force occurred before moving. Before earthquake or before landslide, Newton force have been existed. So this another meaning is that the Newton force, Newton's second law. What is the Newton force? Newton force created by the deformation, created by the Hooke's law. So this is a simple formula to give a relationship between two laws. So this is the first law. And the second formula to give even the Newton force occurred before moving, we should observe the curves to show the experiment of physics just now. So we should have geodisaster. What is precursor? Precursor is dropping, delta F. That means before earthquake, the moving precursor. What is precursor? Precursor is the dropping. Dropping means delta F. And because precursor we found it, we should give a third formula. The third formula to show how long for the time between precursor and earthquake and landslide and moving. So this is very important. And this precursor time is related to the M. M is the weight of a sliding body, and is the weight of a footing wall or the hanging wall, just like. If M is larger, the time is longer for prediction. If it's a short, it's a lighter, maybe it's a smaller, maybe it's the time is shorter for that, for prediction. So this is, and also another parameter, the U. U is the behavior of rock masses or crust. If it's brittle material, the T is shorter. And if it's sedimentary rocks, maybe the time is longer. So this is a formula meaning. And also related to, time is related to the Newton force. Newton force, if the larger, the time is shorter, it's smaller, and the time is longer, just like that. So this is a meaningful three formulas, right? So we have found the solution for the description of the mathematics in the dark area. And after those problems solved, we set up a monitoring system. And here is a show a Newton force variation measurement system. Active force, for the plane or slip. This is a landslide. The slip surface. Very important is that whenever slip surface or the active fault surface, we need to cross. Our system should cross the surface. And you can see every strings here. Just like we put the piano there, every piano have a different strings. What it means here, strings? Strings is every piano have strings. That's strings with pre-stress. Also, similar here, every strings here have pre-stress. Pre-stress make a string here very sensitive. Not only the moving, but when you have a change of moving, the sensors know. So the sensors at the top of pre-stress strings here, and the sensors here give much information. When the landslide or earthquake happened, when moving happened, the process of moving, and the sensors give parameters to describe this moving, and the information from sensors to the base station, and base station reflect the signals to the satellite, and satellite give information to the processing center in laboratory. And laboratory computer can firstly get the information from the field, and then to set a database, and also treat it by formula. And finally, we get a curve of a Newton force variation with time. So this is a story about this principle. And firstly, the system produced in 2009. And this is the hardware system, the components installed in the field. And this hardware components too also show in the field and in the room of the laboratory. And this is how works for the system. And every minutes or every hours give a date. And then the computer give curves to show the variation of the Newton force. Variation. So applications. We do the two types of works. First, we monitor the Newton force variation for the landslide, and other work related to the active fault. So firstly, we give a result about the slip surface, the Newton force variation in the everyone now know that the landslide prediction is also the difficult problem worldwide, not only in China. Several cases. Among the 1,000 points, we have got 15 landslide process curves. You can see different shape. A red color curve to show a variation of Newton force variation. And the blue color to show the rainfall. And everyone knows that rainfall related to closely with landslide. So we carefully to look a shape of curves. Different curve have different shape. That means to show the different geological condition, hydrogeological conditions, and engineering conditions, and different climate. So the different shape of curves. But even the curves is different, but also one point is say when dropping happened, and then landslide happened. These regulations firstly take out from the experiment in laboratory. It's the same as that in the laboratory. So, and so many curves here we only show a part of them. We have completed the curves for landslide about 15. And here give a table. How long for the prediction time before moving. And we can say the first line is the time is the date of a landslide, and the second pillar is a scale, how many meters of a sliding body. And the third third column is Newton force, the time for the Newton force dropping. That means the precursor happened time. And after several hours, the landslide occurs time. And what's the difference of a time? And we can see the last curve to show the shortest is about 2 hours. The longest is about 20. That's maybe I can repeat later. The final line, the final column to show the time difference between the dropping time and the landslide time. The shortest one is about 2 hours, and the longest one is about 20 hours. So for landslide, we can have a 2 hour and 21 hours before moving. We can give a prediction, and because we can do this, so a lot of people escaped. The table show how many people escaped from the dangerous area for each event, and how much for the cost of equipment withdrawn from the dangerous area. So totally now for 15 landslide prediction, 312 people escaped from, saved from the event according to the statistics number. And another works that have been done by the monitoring of active fault. Up to now, totally 24 monitoring points distributed in 11 active faults in China. And I can tell you that each point system, because the active fault is very deep. One system is more than 100 to 200. The deepest one is about 300 meters. So the need costs a lot. So the point is much less than that of landslide. So this is the reason for that. Even so, we still have 24 points for active fault. And here we show the case one is Zhangjiakou is active fault. This error is a side very dangerous for the earthquake. So we give 2 points there. You can see the system to show the system cross the active fault. And also for 2 points, the 2 curves to show Newton force is a safety because of Newton force doesn't vary, it's a constant. And also the Fujian active fault. It's Shanxi province, Fuxian, Fengxian active fault. So also to show the horizontal, non-dropping happens there. So this is another fault. This Jinzhou. Jinzhou is you know in eastern of China, very large secure active fault means low, maybe a very large active fault there. So we put the points there. And I can tell you that for 24 points, for 11 active fault, no any earthquake happened there. So we got the active fault not very active. It's stable. So the variation of the Newton force is a constant. It's a horizontal. So at last, I would like to give some words about the conclusion. The dropping of Newton force is a precursor of a landslide. It has been already proved by the practice of a landslide prediction. That means this phenomenon and can be proved by the laboratory, also proved by the laboratory test. Also proved by the practice. So in China, we have a lot of applications for this method, and also we start to install the server in Hong Kong area and in the maybe in the foreign countries, South Africa. And in next step, and the second conclusion can see that the dropping of the Newton force in laboratory, we can prove that it's a precursor of an earthquake disaster. Have been already proved by physical simulation in the laboratory, but it couldn't be proved in the practice. But I hope will be proved by the practice in the near future. So this is what I want to say. According to we studied above, we have published a paper. The paper's title is the cross-fault Newton force measurement for earthquake prediction, published in the Rock Mechanics Bulletin. And this is the first paper of this journal. Remember that 20 paper published in the 22 October. 4 months later, or half years later, 6 months later, one commentary papers published in King's College London, in Journal of Geology and Geophysics. This is a famous journal. And the author is a professor, Nick Druck. Nick Druck is a professor in King's College London. And he wrote a commentary paper in this journal. The title is Cross-Fault Newton Force Measurement, a potential tool for earthquake prediction. So you can read one part is the same as our title of the paper. So a potential tool is a very good ideas, I think. Very good words for this paper, I think. And we remember that American scientists Robert and Taylor, who is now is Taylor is a professor in Tokyo University of Japan. And in 1997, he published the paper. Several authors from the American published a paper in Science in 1997. This paper's name, Earthquakes Can't Be Predicted. So those two papers, the American papers and the British paper, so shows a different idea. For me, I agree with this idea from the London, from the NAC drug. I agree with his idea. So this is what I want to say. Thank you for your attention.
Thank you. 黄老师，
哎，你好，
你好，黄老师，你好。那个黄老师，any questions from the audience? I mean, it's very interesting talk. That seems that the earthquake prediction is possible, and according to Professor Hall, he says going to be proved too. 谢谢黄老师。So maybe 张老师你在吗？
Yes, I'm here.
Yeah, because I want the Professor Hall， 我让何老师也听你的讲，之后你们可以来对谈一下。那个我不知道黄老师去哪里去了。Professor Huang, are you still there? I don't know. I have not heard from her.
好，我在。
So why don't you
我只
introduce
是
Professor Zhang?
我现在对照着我刚才展示的，在缅甸地震之前，云南丽江观测到的断层的因变释放，就是那个体积因变的这个突然的降低，然后再对照刚才何老师讲的牛顿波斯这个下降，然后是作为地震的前兆，我就在想，是不是这个牛顿力下降，就是因为断层的因变的释放造成的？我现在是这个问题。然后，如果是这样的话，那么这个它的物理就有可能是因为因变的释放而导致了一个应力的下降，最后让断层开始运动，就产生了牛顿力。所以中间这个应力降是因为因变的释放造成的，是这样理解可不可以？我大概是听了这个。
我 in Chinese, in English. I would like
in English. Yeah.
I would like to say something in Chinese because my Chinese level is much better than that of English.
Okay, my question in English. Now, repeat. The nature of Newton force, the force drop along the fault. The physics nature of the force drop is the strain release along the fault. Is that a big question?
Yes, Professor Huang's question is a key point for my topic. And what's the mechanism of dropping? Dropping is the precursor for earthquake, but what's the mechanism of dropping? And according to our studies in the laboratory, we have the same conclusion with Mr. Huang. It's before failure, before broken, before earthquake moving, strain release must be had. So this is very important. And the difference between the strain measure and the Newton force measure is strain measure, and stresses measure is a point measure. But Newton force measurement is a joint force measurement. Joint force means resulting force. There's a different from it's a surface. It's in the slip surface. Newton force variation. So, but it's a strain monitoring and strain stresses and force have a very strong relationship because it happened in the one system of a mechanics of an earthquake. So I agree with that your idea. Is caused by the dropping caused by the strain release. Yeah, thank you.
Okay. Yeah.
我可以用中文跟你讨论吗？
We can continuously discussion
We can discuss later. After
meeting.
After the meeting, we can discuss in detail. Thank you very much.
Okay, let's hear what Professor Zhang has to say. 张老师
I'm here.
Yeah, okay, go ahead. Thank you.
First of all, I'm very honored to be here. That's invited by organizers. Thanks, Drs. Huang and Yip. And today, what I would like to share is, as you can see in my title, I would like to talk about how Taiwan built up such kind of resilience community in respect of, at least as you can see, there are three components over here, what we can do before, during, and after earthquake. In respect, as you can see, there are three pictures over there, which shows what we can do in respect of the probability, seismic data, and risk assessment, and earthquake early warning, and aftershock forecast. That responds to what we can do in different periods. But first of all, I would like to emphasize the importance of building up such kind of resilience communities by demonstrating that two cases of the earthquake occurred in Taiwan region. One is, as previous talk already mentioned, 1999 Chichi earthquake. When everybody was still young, at that moment I was a college student, and I expect that all of the Taiwanese remember that such kind of disaster, which result in a lot of the damage and building damage as well as fatalities. As you can see, I just make some of the summarization for the total number of fatalities and the collapsed buildings. 25 years later, another earthquake occurred in eastern part of Taiwan called the Hualien earthquake that the Dr. Huang also introduced something about this earthquake. That earthquake is also very, very large. But if we take a look, if we compare with these two earthquakes, we found the magnitude are similar. One is magnitude 7.6, another one is 7.5. But if we compare the consequence, we will see the number, no matter that is the number of the fatality or collapsed building, it shows the Hualien earthquake has a significant lower impact to Taiwan. Of course, if you know the distribution of the population in Taiwan, you can argue that in eastern Taiwan, we don't have so many populations that result in a smaller damage. But still, we can see such kind of comparable size of the magnitude result in significant difference of the fatality as well as the collapsed building. That might infer that in the past, say 25 years, we, Taiwanese, has done something good toward resilience communities. Such kind of the result also echoes what they found, what a global earthquake model found. So global earthquake model is an NGO that's responsible to assess seismic risk around the world. They have the duty that to announce some of the loss estimation for each of the large earthquake occurred around the world. Of course, including 2024 Hualien earthquake. This is the snapshots that I attend their webinar. They claimed significant overestimation of their fatality as well as building damage. Of course, here I don't want to complain their assessment, but I want to emphasize maybe there's some differences between the model as well to the reality to Taiwan. Maybe in Taiwan, we have done something right to significantly mitigate the impact of the seismic risk. In order to clarify such kind of a situation, I would like to discuss with everybody what are the major components of the seismic risk, why some buildings collapse and others don't. So, of course, there are a lot of the answer in respect of the engineers, seismologists, or seismological engineering. But I would like to just use a very, very simple term for public science. So this is a snapshot of the after the scenery after the 2022 Qishan Taiwan earthquake. So one building, as you can see, collapsed. So here I raised at least 3 components. If one building collapses, of course, obviously there should be an earthquake. Second is, if one building collapses, that must be some buildings over there. And the third, you can see in the middle of this photo, one building collapsed. But you will see for the surrounding building, its survival. And I would like to draw your attention, especially the figure to the left. This building looks not very, very strong to the severe shaking, but it survived during this earthquake. So there must be something wrong to these buildings. So this is how we assess seismic risk assessment. For more scientific term, I just transfer such kind of 3 components into the seismic risk assessment. So that means if we would like to understand or estimate potential seismic risk, we need to know the hazard, exposure, and the vulnerability, which represent how the behavior of earthquake, the building exposure, the distribution of the building, as well as how strong of this building does come to sustain from severe ground shaking. By integrate these 3 parts, and then we can assess seismic risk. Before that, I would like to share some of the situation in Hualien. So here are 2 photos represent the buildings in Hualien. The figure to the right, as you can see, that is very, very old building. I don't know the exact age of this one. And this is kind of the wood structure. Looks like very vulnerable to the earthquake. The figure to the right, as our understanding, this building was built 27 years ago before the earthquake. And this is the RC building, as known as a reinforced concrete building. Guess which one should be more seismic resistance, an old wood building or new reinforced concrete? You can just keep your answer in mind first, and I will announce the answer. But before I announce the answer, I would like to tell you why I cares about the age of the building. Because in the past decades, we have several generations of the building codes. As you can see, from 1973, we have the first generation of the building code. So after some of the upgraded, one part I would like to remind you is after 1999, as I mentioned, the Chichi earthquake, our government modified our building code, and so that means all of the buildings built after 1999 should follow such kind of the new generation of the building code, which should be more resistant. So that's the reason why we have some collaboration with some of the governmental agency, NCDR, National Research Center for Disaster Reduction. So based on such kind of the collaboration, we try our best to establish a first generation of the building database. That means we first want to know the location of each building. So that's the reason why we have such kind of the building polygon obtained from National Land Surveying and Mapping Center. And then we obtained all of the building parameters, including building age and the building structures, according to the text data. So according to this one, then we can understand the exact building age and the building structure, as well as the building geometry, based on using such kind of database. According to this one thing I would like to mention to you is approximately 22% of the building was built after 2000, which, as I mentioned, which might be more sustainable from the earthquake damage. After obtaining such kind of database, we can just superimpose the distribution of the damaged building, and then we can understand where the damaged building are, and the second is what are the building parameters, including the building age and the damaged building structures. So by comparing two kinds of the data set, and we can understand the general distribution of the building taxonomy, as well as the building damaged buildings. So I don't want to say too much in detail, but one thing I would like to emphasize is, according to the concept of the statistics, if the building should be the damaged building is randomly distributed, the total percent of the building and the damaged building should be more or less similar. If they are higher, means such kind of the building parameter will be more vulnerable to the earthquake. So as you can see, orange one represents the damaged building in the Hualien event. The blue one represents the total building in Hualien. So surprisingly we found, not surprising. First is after the building after 2000, the damaged building the percentage of damaged building is significantly lower, which suggests that the importance of the modification of our building code. But we expect the building without building code should be more vulnerable. But surprisingly, we got more damaged building for the period in between 1973 to 1999. If we go back to the figure I just showed to you, here are the current situation of these two buildings. As you can see, figure to the left, it survived after this earthquake. But figure to the right, which is not as old as the building to the left, that building was built in between 1973 to 1999 with RC structure, and it was collapsed during this earthquake. Such kind of information have some of the hint. We can further assess seismic risk by further understanding of such kind of the exposure as well as a vulnerability. By using this concept, then we would like to assess the detail of the seismic risk assessment before the next great ones. So that means we first have the distribution of the ground shaking during the 2024 Hualien earthquake. We have the built-in exposure database as I just introduced. We also have the distribution of the damaged building. What we don't have is the vulnerability for each of the different buildings, or more specifically, a building taxonomy. So we just make some of so-called inversion, and we obtain the best fit of the fragility curve considering the distribution of the damage. After having fragility curve, then we can do the further seismic risk assessment for not only Hualien, but also for the entire Taiwan region. So then we try our best to establish the building exposure database by using some of the imagery identification using the satellite image, as well as very, very famous AI technology as known as aka mask RCNN. Then we can identify the distribution of the building taxonomy by superimpose of all of the information that we obtained from some of the best available data, including township household count. Then we can distribute the housing parameters for each of the building parameters. So then we can establish the Taiwan-wide the exposure data. As I mentioned, if we would like to assess seismic risk, we also need to understand seismic hazard. Fortunately, Taiwan earthquake model has published the previous version of the seismic hazard map using some of the state-of-the-art database, including the active fault parameters as well as the ground motion prediction equation. Furthermore, they consider the side effect. Then they establish such kind of the seismic hazard map. So such kind of the result will be perfect input for our risk assessment. By superimpose all of the information, as I mentioned, the figure to the right, then we can establish the seismic risk assessment for entire Taiwan. As you can see, for some region, for example, in eastern part of Taiwan, because of the lot of the earthquake occurred here, it has a very, very high hazard. By contrast, for the northern part of Taiwan or southwestern Taiwan, as long as we don't have significant high hazard, but because of the very high density of the population, eventually we have relatively high seismic risk, which will be a warning signal for the population over here, which is Taipei City, a city of the million of the people live here, including my family and I myself. So that's the reason why we need to further detail of our seismic risk. But the question will be how? After I introduce how we establish the exposure as well as vulnerability data, we need to propose the beta version of the seismic hazard assessment. As I mentioned, this hazard map was built 6 years ago in 2020. So after 6 years, we need to propose the better understanding of the seismic hazard. So that's the reason why we try our best to integrate some of the information from seismology, geology, geodesy, engineering, seismology, and so on and so forth to propose a next generation of hazard map. What seismology provides us is to integrate all of the available data. So that means not only the log from Central Weather Administration, which is official bureau of the earthquake announcement in Taiwan. We also consider JMA or some of the international organization. They by integrate all of the information, we obtain the seismic earthquake catalog not only in Taiwan but also in the surrounding region. By defining the area source and determine the Gutenberg law as well as A and B values, and then we can understand the distribution of the seismicity level for each of the region. This is how our seismologists has done. For geologists or geomorphologists, they propose the first generation of the offshore seismogenic structure, or aka active faults. So that means for some of the region, for some of the alignment which shown in red, suggests that the slip rate is relatively high, as you can see some of that in the eastern offshore of Taiwan. For others, as long as the activity of this offshore seismogenic structure is not so high, since it connect to the inland active fault, it could result in relatively higher hazard, which could produce higher magnitude of a coming earthquake. That is what we need to be aware of. Not only for offshore structure, we also modify our inland active fault database. We modify some of the active faults in southwestern Taiwan, and we also propose a time-dependent model. That means we need to consider the last event of each of the active faults. So that means it is relatively unlikely to occur another earthquake in the coming future if one earthquake just occurred. For example, the Chernobyl fault occurred 27 years ago. So considering the recurrence interval of this fault is approximately 300 to 400, it is unlikely to occur another earthquake. By summarize all of the information, then we can obtain the impact of the inland active fault to the seismic hazard. We also have some contribution from geodesy. So they obtained the GPS data and analyzed the relatively activity for each of the fault by considering two models, including baseline inversion method and the block models. By integrate all of this information, they propose the sum of the slip rate for some of the inland active faults, as you can see over here. By integrate all of this with the slip rate from geodetic information, then we can propose better understanding of the seismic hazard assessment. We also modify our subduction zone geometry as well as its activity. Thanks for the project founded by Thai Power using the Sheck Level 3 methodology, which is kind of the seismic hazard assessment approach, especially for the nuclear power plants, since we have several nuclear power plants, two in northern tip of Taiwan, another one in southern tip. So in order to better understand our hazard assessment, they modify the geometry and the seismicity activity for the subduction interface and the subduction intra-slab events. We also try our best to understand the behavior of the ground shaking, as known as the ground motion prediction equation. In this version, we not only consider the GMPE from Taiwan, but also all around the world. We use some of the weighting approaches and to propose who has the better performance for the ground motion prediction in Taiwan. So by considering their performance, as you can see the figure to the left, and then we propose some of the logic tree considering different weighting for each of the GMPE models. By summarize all of the contribution as I just mentioned, so as you can see, there are so many Taiwans over here. I don't want to say too much in detail how are their impact for each of the individuals, but I would like to draw your attention to the figure to the largest Taiwan to the right. Some part is because some increase of the seismic hazard is because of the area source, but for especially a significant increase of the hazard in southwestern Taiwan, which is location of the Kaohsiung and the Tainan city, the two of the largest city in southern Taiwan. Such kind of the high hazard is because of some newly identified structure, including the southern Zhongzhou structure and so on and so forth. Such kind of information will be better understanding how high hazard or relatively high risk for Taiwan, which will be very, very important for us to be prepared for the next great ones. Such kind of information can be also applied for engineering purpose. So this one, as example, we applied to some of the green energy. For example, we have a lot of the offshore wind farm in western offshore of Taiwan, just in between mainland China and Taiwan. We in order to assess their seismic hazard, we have some collaboration with engineering consultant companies and try to evaluate the impact of the earthquake to such kind of the wind farm region. We also do the hazard assessment for the water reservoir. So this is the Wushantou Dam, which is in southwestern Taiwan. We try to identify the location of the surrounding fault called the Liujia fault, as you can see the red dashed line, and to evaluate the impact of this earthquake. We also have some of the interaction with governmental agencies, try to assess the potential risk to some of the urban region. So this one, as example, this is in the northern tip of Taiwan, and we identify there is one fault called the Sanjiao fault, which is just the eastern part of the Taipei city. We try to simulate what if when one earthquake occurred in this region. So after estimate the corresponding ground shaking for the Sanjiao fault, we have such kind of the working group with ANPRI and the NCDR, who are the governmental agencies responsible for the seismic hazard or all kinds of the natural hazard risk assessment. They evaluate potential consequence for such kind of the waveform simulation in respect of the building damage, causality, and the water supply system damage, and the road bridge damage. Such kind of the evaluation doesn't just want to scare people. We want to tell people how bad it will be when such kind of the next great one comes. So such kind of the information will be very, very helpful for some of the stakeholders to prepare for the next big one. For example, these two photos represent the earthquake drill and the strategy planning during our National Disaster Prevention Day for every September 21st. So that is how we deliver our research knowledge into governmental agencies as well as industry. So this is how we can do before one earthquake. Think about this. we know in Taiwan, earthquake happens. But what we can do during one significant earthquake? So people can immediately think about earthquake early warning, just as the previous talks just mentioned. Let me clarify, earthquake early warning is not prediction. Actually, earthquake already happened. Just the strong shaking hasn't come yet. So we just use such kind of earthquake early warning system and to warn some of the sites far away from the epicenter or hypocenter, and to do some of the warning, as you can see the snapshot from my phone, which represent the earthquake early warning when one severe shaking is coming. In order to do this, in order to enhance our EEW system, we need to do some of the preparation in advance. For example, we need to better understand the behavior of the ground shaking, aka ground motion prediction equation, GMPE. So that's the reason why we have some collaboration with Central Weather Administration, try our best to understand the behavior of the GMPE in Taiwan. This is what we can do. But the reality is, if we are talking about the 2024 Hualien earthquake, as you can see, the picture to the left, for many of the region, including latter place of the northern Taiwan, the CWA did not announce the EW alert. The reason is why? Just because of the underestimation of the magnitude and then underestimation of the ground shaking, then result in the failure of the EEW. After this kind of the experience, we need to think about, by contrast to the traditional EEW system, what we can do further in advance to enhance our system. So in order to solve that, our team collaborate with, again, the Central Weather Administration. This time we abound the traditional idea, but using more fancy way, AI. So that means we don't predict, we don't locate the location of the epicenter. We don't estimate the magnitude that might result in under or overestimation of the ground shaking. We directly identify the image and predict the potential ground shaking. So I don't want to say too much in detail, but eventually we just use this kind of the concept, especially applied to the 2024 Hualien earthquake. So as you can see, the figure to the left represents the actual shake map that recorded by CWA. The figure to the right represents how we predict the potential ground shaking after each of the time snapshots. So that means even though for some of the region haven't yet encountered any shaking from the earthquake, they can learn from the previous experience or learned from some of the station closer to the epicenter, and then deliver some of the information to the far field. So generally, it shows for the most part of the Taiwan, it could encounter the intensity 4, which is the threshold of the earthquake early warning system. So such kind of information provide us a hint that we might better issue the earthquake early warning systems. And I'm very happy that our result has just published in JGR in the early of this year. So if you are interested in that, please take a look at that paper. So after occurrence of the earthquake, we might encounter a lot of the aftershocks. So that's the reason why we need to think about if we can forecast the distribution of the aftershocks in respect of the time and the space. So again, the figure to the left represent some of the reality after the 2024 Hualien earthquake. The 2024 Hualien earthquake as well as the 1999 Chichi earthquake. That means when one very, very large earthquake occurred, we might expect some of the consequent aftershocks, which might be very, very large. What is worse is if that large earthquake is just a foreshock that might lead to another next great ones. So this is why we need to know some of the information as I list over here. People always ask after one earthquake, how long the aftershock lasts, how many aftershocks will occur, and how large of this the size of the aftershocks. And then what is worse is will another large earthquake occurred after such kind of giant one. In order to answer this one, my colleagues and I just proposed the so-called ETAS model, which is very, very, very famous for forecasting earthquake. We just try to integrate what already happened before and try to forecast what is the next. Such kind of ETAS model is the basic concept of the ETAS model is very, very, very simple, which is based on the Gutenberg law or Morris law represent the decay of the aftershocks. So by integrate all of the information, then we can better understand the distribution of the aftershocks. As you can see, when one main shock occurred, we have the hotspot of the earthquake forecasting in Hualien region, suggests that the occurrence of the subsequent aftershocks. Several hours after Hualien earthquake, we have the better understanding the spatial distribution of the aftershocks. Then we can better understand the potential distribution of the potential aftershocks. Such kind of information will be very, very important, especially for those who do cares about not only severe ground shaking but also weak shaking. For example, in Taiwan, we have a lot of the precision industry, such kind of waveform, as you can see over here. Such kind of waveform will be very, very vulnerable, even for some of the minor ground motion. So that's the reason why we do need to propose such kind of the infrastructure to forecast the distribution of the aftershocks. Such kind of information will be also useful for some of the geosite in respect of any kind of the drilling project, for example, geothermal and so on and so forth. The major reason why we consider this is, as you can see, the figure to the bottom left represent the sum of the damage earthquake occurred in South Korea with magnitude 5 point something. Not very large, but the reality is this earthquake is triggered by geothermal development. So that means such kind of geothermal development or CCS, as we know, both of them could trigger some of the seismic activity. Using such kind of earthquake forecasting could monitor the potential of the seismic hazard in the coming future, which is some of the fundamental idea for us to reach such kind of the carbon net zero, such kind of the green energy policy. So by summarize all of my talk, what I would like to deliver to you is try our best to propose some strategies for the resilience community, no matter that is before, during, and after earthquake. Unfortunately, in Taiwan, we will always encounter the next great ones. But the question should be, have we already prepared before that? So this is my talk. Thank you very much.
Yeah, thank you very much, Professor Zhang. It's very, very interesting and detailed talk. And then maybe you should give another talk next time. I wrote to Kenji. Kenji, are you there? Kenji?
Yes, I am here.
I asked you to make some remarks. Can you do that?
Okay. Well, thank you, Sheng. That's very interesting. Well, yeah, it's important to say that the damage is not only for the hazard but also the exposure. In exposure, you include the building type or like a year, right? That's it's a part of the exposure.
Yes.
Yeah. Okay. I'm still wondering why, for the Hualien case, the damage, you have some damage, but building damage is significant, but the human damage is very kind of minimum, right?
Yes. If we are talking about the build first, if we take a look at the fatality for Hualien case, as you can see, the figure to can you see the slide?
Yeah.
Okay. The total fatality is 18. So generally for the classical seismic risk assessment, we can just transform the building damage into and further evaluate fatality. The situation for Hualien case is those 18 fatalities are mostly due to landslide rather than building damage. So that's the reason why it is rather difficult to just transform the building damage into fatality, especially for the Hualien case. So that means only one person was killed due to collapsed building. So that's the reason why in the Hualien case, I don't say too much about the fatality because of the significant bias to the landslide.
Landslide?
Yes. Yeah. So that means for most of the fatality take place in Taroko National Park rather than urban city.
Oh, I see. Okay. Well, I'm thinking that the first talk and Professor Harold discussed about the earthquake prediction, and you also mentioned the earthquake early warning. Okay? So if the earthquake is predicted or early warning is made, that may save people, but building cannot be saved, right?
It's true.
Right. So the building collapse, we cannot avoid earthquake, building damage by earthquake prediction or early warning. But the only thing we can do is just warn the people to escape from building. But how about for the landslide? Well, maybe, yeah.
To respond to this, I would like to first especially want to emphasize the importance of the building quality, aka the building code. So that means in the case of the Hualien or any kind of a case in Taiwan, we understand that the importance of the building code. As you can see, the damage for the beta quality of the building significant is lower than those before 1999. So that's the reason why I fully agree with you that people can escape, but building cannot. And the second is, in engineers, we always say, earthquake don't kill people, but buildings do.
Yeah.
So that's the reason why I especially emphasize the quality or more specifically, the vulnerability of each building. So that's the reason why I would like to emphasize for this part.
Yeah, I agree. But you also mentioned about landslide. And I understand that the landslide was also the Wenchang earthquake was a major reason for the damage, right?
Frankly speaking, the landslide I mentioned is during the 2024 earthquake. As you know, I definitely not a landslide guy, so I cannot comment too much about that. But the reality is our team, Yijun, had some of the specialists about landslide. So that's the reason why we wish in the coming future we can integrate different components for such kind of the plural hazard or secondary hazard, including you yourself for tsunami and the Professor CTB for landslide or Professor Jia Jundong for liquefaction as well as the landslide. This is our strategy, but we are still working on that.
So that is related to the first talk, Professor He, that he showed that landslide kind of prediction and earthquake prediction. So how about for the landslide caused by earthquakes that can be also similarly predicted, or is the first speaker here, or I don't know.
Professor He院士，你在吗？
I can't hear you.
Yeah, can you comment on that? Follow it up, I think some discussion.
Yeah, I try to answer your question. A landslide, you just mentioned the landslide caused by the earthquake, how to predict it.
Yes.
Whenever caused by earthquake or caused by other area, if the landslide happen, they obeyed Newton's second law. So the variations of Newton force in the surface of a slab are very important for prediction. So I think the landslide caused by earthquake also can be predicted if you install the system there for monitoring of Newton force. Certainly can have a good prediction result, I think. Thank you.
Well, I think your model is like even for landslide or earthquakes, it's just that you have a kind of strain accumulation, and then eventually in the Hooke's law into like a Newton's law or sudden big event.
Yeah.
But for the landslide generated by earthquake, maybe have different mechanisms. That maybe landslide may be caused by shaking, right? So
yeah,
mechanism may be different.
You know, equilibrium state, the very potent. Whenever the dynamic force and static force acting on the surface of a slab, that's a same result. The equilibrium state. If the balance destroyed, the broken, that's start the slide. So the method of the dropping means just a broken balance state. So I think maybe it's a mechanism for failure, for moving is the same. Because moving is a dynamic process. So I think but after now, we have no any case for prediction of landslide caused by earthquake. But I believed it can't be predicted, I think. This is my point of view.
Okay, thank you.
Thank you.
Thank you.
Thank you.
May I comment on that?
Sure.
Uh,
I mean, no, it's not my.
Yeah.
I'm done.
Re-
Yeah,
re-
I'm done.
Regarding earthquake trigger landslide, I have two suggestions. One is actually, as you can see, this is the probabilistic seismic hazard map. That means this is a potential of earthquake that might affect Taiwan in the coming years, say 50 years. So that means as long as we cannot predict earthquake, but we can summarize some of the potential of the earthquake in the coming future. So that means such kind of information will be very, very important for us to modify our building code. Actually, there's another map called the probabilistic landslide hazard map. So that means they summarize everything, including earthquake triggering, including slope, and any others parameter that might affect landslide, and then propose this is in probabilistic way that could warn people where has a higher potential than the others. So that kind of the probabilistic landslide map will be very, very helpful for the long-term preparation. If we are talking about the short term, that might be some kind of the prediction or forecasting or precursor or just early warning. So in Taiwan, as I remember, there are at least two groups. One is from Academia Sinica conducted by Dr. Xinhua Huang. He used optical fiber, use stars, and have very, very high precision of the sensing, have the better understanding some of the migration or creeping before one significant landslide. Another group is from the National Yangming Jiaotong University, by Dr. Zhang Ruiming and Professor Wei Anzhao. They use some of the traditional seismometers to monitor the landslide signal and use AI identification to figure out some of the signal that might be the precursor for the landslide. So this is generally what I expect we can do for landslide before and during landslide.
Okay, any further comments from the, actually, I would like to see whether any question from the audience, from the participants. You could either raise your hand or just ask.
Whether I can say something.
Yes, please.
About, for prediction or early warning for landslides and earthquake, generally says geodisasters. Geodisasters covered the two main types of landslide and earthquake. And up to now, we have a lot of method to do the monitoring work, to try to find out the good answer about the prediction. And several methods. The main method is displacement, created by the Taisaji in 1923. And another type is geophysics, just like Professor mentioned, geophysical method, maybe acoustic method and magnetic, electric, so on and so forth. So many methods to measure about the field changes, field of physics parameters. And also, we mentioned the Newton force measurement. This third type for that. So mainly, so much method so much types of method. But according to our research, we believe that geodisaster process is only belong to the mechanics process when rheostatic balance and dynamic. If moving happened, it's belong to the process of dynamics. So the mechanical system related it's very close to the nature of a geodisaster. And I think finally, what method related to the mechanics, for example, the deformation and the displacement, and the stress and the strain, is related to the mechanism. And I think those only a point information. A point information is related closely to the prediction of a system. The earthquake and the landslide are the process of a system failure. This is very important. Information at one point couldn't be predicted. And so we start to focus on a system of mechanism. So Newton force, according to second law, if you somebody moving should be obeyed Newton force as a Newton second law. So Newton force is very important. This is one point. Another point is that if you want to have a very good prediction scientifically, you should make every parameters satisfied two conditions. First condition is the essential condition. Second is sufficient condition. What it means, for example, the deformation. Earthquake and landslide happened. The deformation must be had. But the deformation happened, displacement happened, occurred, not meaning the landslide or earthquake happened. So this means that it is essential, fitting for the essential, but not fitting for the sufficient condition. But the Newton force fitting for the both. It is sufficient fitting for sufficient condition and essential condition together. So this is a case. So we just mentioned the displacement, deformation, stress, strain, and the water level, and geophysics parameters changing. It always belongs to only fitting for essential condition, not fitting for the sufficient. So this is a key point. So thank you. This is my point of view. Thank you.
Yeah, thank you. I just very strange ideas keep to my mind, and then I want to know if we can use multiple observation techniques to transfer the observation to the Newton force. It's just a strange idea. So I think Professor He's Newton force for the fault slip prediction is very useful information and a new approach to try to distribute the other big faults like the sky faults in such faults in Myanmar. Maybe we will try to promote the cooperation with Myanmar scientists. Is there some scientists from Myanmar? Originally, Melson promised to join here. Maybe we can promote this cooperation in other big faults to apply the Newton force measurement to the local earthquake prediction in the future. It's one of the objectives of the strong earthquake group of AOGS, RAC. Okay. I say this one. And also Zhonghan's work. Yes, Zhonghan's work. So useful to apply for the other countries and regions with fewer consideration of the seismic hazard maps. For example, the Venezuela's, yes, the buildings, tall buildings crest in Taiwan is a fewer event here, right? So your experience can distribute to other regions, and Professor He's Newton force measurement also can apply to the big faults. For example, in Taiwan's Hualien, the east of island, yes, the big fault in central Chelongpu, maybe. Right? Yes. So today's talk is useful, is meaningful for application to the regions or countries with big fault, and to the regions and countries with fewer consideration, very small consideration of seismic hazard map, PISA, or other measurements. This is today's proactive measures is useful, is meaningful to apply to application for others. Okay, so with proactive measures, we still can coexist with earthquake risks. Okay, that's my objectives for today's talk. Is there any other opinions from Professor Ye?
No, I think that I'm happy, and everybody have a chance to discuss. And, yeah, and we will Professor Zhang, Zhang Zhonghan, you promised to find us one or two European speakers, right, next time?
Yeah, because as I mentioned last week, I traveled to Croatia in Europe and to attend a global earthquake model conference. At that moment, I encountered a lot of people in respect of the specialists in seismic hazard, seismic risk, and so on and so forth. Unfortunately, at that moment, that is so close to this webinar, so that's the reason why they declined to attend this seminar, but they promised us that they can attend the next one.
Mm-hmm. So because of the time difference, I think the next time, the number 3, we probably should dedicate it to European scientists, because it's hard to accommodate,
Nice.
at the same time. So let's try that. And Kenji, if you find someone interesting, let us know. And also, of course, Professor Huang, if you find some outstanding European scientists, and please let us know. So we try to put the program together, and maybe in one month's time. Okay. And thank you so much, and have a nice weekend to everybody.
Thank you very much.
I think it's a very interesting webinar today. And thank you, Professor Hao Yuanshi, and Professor Zhou.
Thank
Thank you
you，
very much.
谢谢，
谢谢啊，侯老师，
Yeah.
感谢。
谢谢教授，谢
Thank
谢，
you.
Okay.
欢迎
周末愉快。
欢迎你们有机会到北
Nice
京。
weekend. Yeah. So keep contact, keep exchange. Okay.
拜拜。
Bye bye.
Bye.